The next case turns out to be very important for controlling the change in acidity resulting from the addition of either a base or an acid to a solution. And as we'll see, it will evolve into something called a buffer solution. A buffer solution is a solution that resists large changes in pH via the addition of either an acid or a base. And it's these buffered solutions that are so important for a living organism, because the pH balance in your body, for example, has to remain within very, very tight limits, or it's extremely destructive of any living organism. So let's take a look at the addition of a salt containing the conjugate base. So let's start out with what we had for case 2 above, where we added a strong base to a weak acid. When we do that, we take our acetic acid, CH3COOH, and we add a strong base, OH-. And when we do that, we produce the CH3COO anion and water. So the equilibrium is pushed almost completely to the right because the equilibrium constant is very large for that. We saw that in case 2 above. So now if we add a strong base to this mixture, the pH will respond dramatically because equilibrium constant is large and it's shifted to the right, so it's the CH3COO anion that dominates in that reaction. So when we add that 10th molar potassium hydroxide, the strong base will yield an OH anion concentration that's essentially equal to what we've added as potassium hydroxide. That is, we'll have 0.1 molar of the OH minus. Now we can calculate the pOH of that. That's equal to minus log to the base 10 of the OH anion. This gives us minus log to the base 10 of 0.1, which gives us plus 1 for pOH. But we also know that we have our good old product of H3O plus and OH minus always equal to 1 times 10 to the minus 14, because the large release of free energy in that reaction drives the neutralization in all of our cases. And you can see that pattern evolving every time we do a calculation. So now we can calculate H3O plus because we have the concentration of OH minus, that's 10 to the minus 1 molar, and that gives us 10 to the minus 13 molar for H3O plus. I can calculate the pH from that. That's minus log to the base 10 of 10 to the minus 13, and that's equal to 13. A pH of 13, that's extremely basic. That is, we've driven the solution from a pH of 7 all the way up to a pH of 13. That's 6 orders of magnitude change. But now suppose we create a solution comprised of a 10th molar acetic acid and a 10th molar acetate anion, which we can do very simply. All we have to do is add the salt, the sodium acetate, to that solution. And if we add acid, H3O plus, to this mixture, the acetate anion will react with H3O plus, producing the weak acid CH3COOH and our H2O product. If we add base, the OH will react with the acid. This is very interesting. So the base always reacts with the acid always reacts with the base. We can immediately write down that reaction. That's CH3COOH plus the OH base, and when we execute that reaction, we produce the anion, the acetate anion, plus water. So let's take a look first at the addition of an acid from the release of acid from, it doesn't matter, HCl, anything that produces an H plus will produce H3O plus. And so when we add that H3O plus to this solution before the reaction takes place, the next thing that happens is that H3O plus is going to react with the negative anion. That is, the H3O plus is reacting with the anion of the acid. And when we execute that reaction, that H3O plus is going to form the acid plus water. And this is where the defense of the intrusion by the acid becomes very important and is protected by the initial concentration of the anion of that weak acid. So when that reaction is executed, what happens is that the H3O plus reacting with the anion produces the acid and a water molecule, the other product. Well, the water molecule disappears into oblivion because there's so much more water in the mixture that we lose track of that. But we know that we produced one molecule of water for every reaction of that acid with the anion, the conjugate base. Okay, so while a weak acid has no defense against added H3O+, we know that, the solution has an ability to defend itself against that H3O+, because the H3O+ reacts with the conjugate base. In other words, the conjugate base CH3COO reacting with that added H3O+ produces the weak acid CH3COOH, and the water molecule, it disappears into the background, and that results in the fact that the hydronium ion being removed. And what's remarkable about this is this first beaker, because when we look at this, this means that the weak acid can coexist in that solution with the conjugate base. And it's the ability of the weak acid and the conjugate base to coexist that sets up the ability of that mixture to defend itself against the addition of an acid, and as we'll see in just a moment, it can defend itself against the addition of a base. All right, we've attacked the solution with an acid. Now let's attack it with a base, and let's see what happens. So in this case, we're going to start out with exactly the same solution. We're going to start out with a weak acid. We know that a small fraction of that acetic acid is going to dissociate to form its conjugate base. So now along comes a hydroxide anion, the OH minus, and it's going to go into solution. And the minute it does, the reaction takes place in which the base, OH minus, attacks the acid, the acetic acid. And we know that in all cases, this release of Gibbs free energy is very large, so that acids and bases react with one another unless they're an acid conjugate base pair. So when we react the acid with the added base, what happens for the final result is that the ability of the solution to provide this weak acid in excess means that when we add the base, we're reacting to remove some of it, but not all. And in this case, the base that's invading represents a reaction between the weak acid CH3COOH and the OH minus. And when that reaction is executed, we of course form the conjugate base and one more water molecule that disappears into the background in this solution. So we removed the hydroxide ion, we've augmented the conjugate base slightly, but the key point is to notice that again the acid CH3COOH can coexist in that solution with its conjugate base. It's CH3COO. And it's the fact that those two can live together in the same solution that provides the basis for protecting that solution against significant changes in pH through the addition of either an acid or a base.